Okay, so greetings everyone. You have joined the event being hosted by the Santa Clara Valley chapter of the IEEE Computer Society. I'm Vishnu Pendyala, the chapter chair. As the largest chapter in the Silicon Valley section of IEEE, we are proud of our over 3,500 subscribers on our mailing list. And we have a robust Twitter following of more than 12,000 followers on Twitter. We hold a unique position due to our strategic location and the wealth of expertise available to us. And thanks to the hybrid mode and virtual mode, we are able to leverage the expertise from all over the world. Like today, we have a great talk being delivered from France. The topic of the talk is mastering product variations by creating a universal language for software customization across industries. So in the world of software and product development, making artifacts customizable for different needs is crucial. So the research community has made great strides with the Universal Variability Language, UVL. It's a tool that helps define and manage these customizations. So UVL is helpful certainly, but it doesn't cover everything. So this talk introduces a new concept called the generic realization language, GREAL. So GREAL aims to fill the gaps that UVL left behind, especially when it comes to applying customizations to the core parts of a product line. And I was just talking to the professor, the speaker, a few minutes ago, and he was highlighting that it is widely used in Europe. So the key features of GREAL include openness, so it's easily adaptable to different industries and uses. It is quite flexible. It can handle various types of customizations. And in terms of declarativity, I think it's quite simple and there are clear rules for customization. It can be applied to multiple projects without starting from scratch. So it is quite reusable. So the speaker will show how GReal works with different base languages like UML, Java, and documentation. The speaker will also discuss a successful large-scale deployment of GReal for business process model and notation at Airbus. So hopefully you'll find this new tool really interesting, and you can know how it can make software and product customization more efficient and versatile. So today's speaker is Professor Jean-Marc Jezequiel. He's a professor at the University of Rennes and a member of the Diver SC team at IRISA, India. Since 2021, he is the Vice President of Informatics Europe. From 2012 to 2020, he was a director of IRISA, one of the largest public research lab in informatics in France. In 2016, Professor Jezequiel received the silver medal from CNRS, and in 2020, the IEEE ACM Models Career Award. He was an invited professor at McGill University in 2022. Since September 2023, Professor is a fellow of the Institut Universitaire de France, IUF. He's the author of 4 books and of more than 300 publications in international journals and conferences. He was a member of the steering committees of the AOSD and Models Conference series. Professor is currently Associate Editor-in-Chief of Associate Editor-in-Chief of IEEE Computer and the Journal on Software System Modeling, as well as a member of the editorial boards of the Journal of Software Systems and the Journal of Object Technology. He received an engineering degree from Telecom Bretagne in 1986 and a PhD degree in computer science from the University of Rennes, France in 1989. So if you have any questions, please feel free to post them on the chat and I'll relay them to the speaker. And over to you, Professor Jazakul.
Thank you very much for the kind introduction. So here we are. So I hope you see my screen.
Yeah, it is taking some time, but yeah, now we are able to see. Yes, thank you.
Okay. So thank you for the introduction. So I'm going to talk today about variability management and where it comes from and what are the issue with that and what is the current status of the research that we have with that. So I will start first by recalling why we're doing that with this well-known issue of the software paradox. And what I call the software paradox is the fact that it is actually extremely simple to write programs. And it's so simple that even you can teach programming to a 6-year-old with languages such as Logo or Scratch. And after a few minutes, he can still, or she can still, she can already write something by manipulating, picture on a screen and doing some loops and some animation and something. So programming is simple. But on the other hand, it's so difficult to write complex software that basically nobody is able to write large bug-free programs. And this is well known for very long. I mean, with this seminal book by Fred Brooks, The Mythical Man Months, that the fact that writing an 100,000 line program is much more difficult than 1,000 times the effort of writing a 100 line program. I mean, the scale makes programming complex. It's not just writing something small is easy, but writing something large is much more difficult than X time the effort of writing something small. And the reason for that is what I call the dimension of complexity. Of course, there is the inherent complexity of software that is due to indecisibility of properties over software that can be dealt with in part with reasoning about the software using proofs or weighted down kind of proofs such as design by contracts or something that is always available, tests. The second dimension is the complexity that is due to the size of the problem, with a difference between the essential complexity, which is inherent to the software, with respect to the accidental complexity, which is due to the fact that there is, you use not the ideal language for the task, or you have to use a whole library, or you have to maintain compatibility and the like. And the way to deal with complexity, I mean, like in every discipline in engineering, if something is complex, you have to cut it into small pieces and to divide and to reassemble them together. And the right way of doing it is to use modularization and modularity to cut things into pieces, develop them, and then assemble back to form something complex. And the way it works, like in any discipline of engineering, is by abstraction, because when you develop a module, it should not be needed to understand the detail of the module to be able to reuse it. That's really the idea of reusing components. And the third dimension of complexity is due to variability and uncertainty, which is twofold. The first is the fact that when you have requirement of a software, there is always variability there, including because business or legal rules can vary depending on the countries. I mean, if you produce software for different countries, you have to address different languages, different habits, and different laws, and also different human behavior. And the key thing there is that it's generally incomplete. You do not, most often you cannot capture everything within the requirements, so it's always incomplete. And moreover, they evolve over time, so they keep changing. So there is an issue there that you develop software on for something that you really don't know exactly what you want to do. And of course, one of the way to address that is with agile programming, where you try to iteratively go towards something that is interesting for that fulfills the need of a consumer. But there is a second aspect of the complexity due to variability and uncertainty, which is the uncertainty about the assumptions about the world, because the program you write is not just an abstract mathematical object, it's something that runs on a computer that use a particular processor, that use particular libraries, that run on a network where there is unpredictability in the delay of the transmission of messages and the like. And it's generally impossible to take everything into account. And so you have this uncertainty that is about the assumption you make about the world that makes things complicated, I would say, from the bottom, whereas the requirements are more from the top. And then you have to write software that works for a non-requirement on something that you cannot master completely, which is the platform. And this is why actually it's so complex to develop software. And of course, for this third dimension, the way you do that is that you try to isolate the part that you do not really know that are going to change or that they are variants with the notion of separation of concern and with variability management. So variability, it can be defined as the ability of a system to be efficiently extended, changed, customized, or configured for use in a particular context. So this is something that is about 20-year old as a definition. So variability is really that. But the core idea of variability is even much older. There is this well-known saying that a set of programs is considered to constitute a family whenever it's worthwhile to study programs from the set by first studying the common properties, the things that are common across all the families, and then determining the special properties of individual members within the family. And that special properties, of course, is variability. And these things come from a paper of David Parnas from 76 in Transaction of Software Engineering. So you see that the idea is nearly as old as large scale software, basically. So what kind of variability you are talking here? I mean, of course, you know it. It's the fact that when you have a product line, when you have a family of software, they have some common parts, like here with the Windows operating system. And of course, because they form a family, there are specific parts because that's interesting for the marketing to be able to, to sell something at more expensive to get more money. And so not all the versions support the same features and the like. So this is one example, but you find that everywhere. This notion of product line, not just in software, of course, you can find that in automotive. You can find that in product-based products where you have very many variants of the same thing. And of course, in software, you have to manage that and to manage this variability there. And this variability is actually a source of complexity because when you have hundreds of variants, of course, you do not want to develop separately this hundred of products. You want to develop only once the common part and just give the delta for describing the various products within the product line. But the thing is that when you have features such as this product should support that feature and this other product should not support that feature and so on, the combination of this feature is exponential. For instance, if you have a system that is rather simple with only 33 features that are supposed to be optional and completely independent from each other, it means that there are 2 to the power of 33 possible configuration, possible product within this product line. And that's basically 10 to the power of 10, which is more than people living on Earth. So quite rapidly, because of this exponential explosion due to the all possible combination of features, the number of possible products grows, extremely fast, and that's very difficult to manage, of course. If you have 320 features, then you have more possible variants than atoms in the universe, which is estimated to be 10 to the power of 80. Okay, so it grows extremely rapidly because of this exponential combination of features. So one way to try to attack that is with something that has been around for now like more than 30 years, 35 years, which is feature modeling. The idea is to capture the feature with that kind of diagrams, that kind of model where you have an eShop that features a number of things, such as it features a catalog, it features some option for payments, some security, and some possibility for search. And the syntax is pretty simple. The black dot says that this feature is mandatory. The white one says that it is optional. And then when you have the payment here, it means that the payment can be either by bank transfer or credit card. And the security there is an alternative. It can be either high or standard, and that's a XOR, whereas here it's a OR. And then you can complement that with what they call cross-tree constraints, such as if you use credit card, then it implies that you use high security. And the semantics of that is just first-order logic, and you can manipulate things like this. You model your features and the dependencies and the like in this way. And that's the basis of every variability modeling language that do exist nowadays. But the thing is that it's only one part of the feature of the picture, sorry, because if you want to actually produce software out of domain artifact based models, based programs, either from code or for documentation or whatever, and then you have this kind of variability model here that describe the possible combination of the feature, then the goal is to be able, by this notion of domain engineering, to work about reusable artifact, the way variability work with that. And then you have application engineering, which is the idea of you make a number of choices. For instance, I want here to select a number of feature and not supporting another number of feature. And I want to combine these domain artifacts with the choice I made to automatically obtain a particular product among all the possibilities within the product line. And so the goal of this talk is to look on ways to automatically derive a particular product from a product line based on a selected configuration. So the starting point is that we have a number of artifacts, which are the things that are reusable. We have a model of the variability with Universal Variability Language or something similar. And then based on that, how do we get automatically a product based on the selection we make and how we configure the software so that it works the way we want. So this problem has been there for 50 years probably. And there are an easy way of doing that, which is called the realization of the variability. How do you handle variability? And the good old way, if you work with a programming language such as C or C++, there is in C this thing that is called conditional compilation, which is basically something called the C preprocessor, CPP, that process your C program before it's actually run into the compiler. And then you can have a number of directives, such as if def a given feature is defined, then you include a specific file. And if this feature is not defined, then there is this particular piece of code that I have to compile. Okay, so this is interpreted before the compilation, and depending on whether the feature is selected or not, then this code is going to be compiled, or this other part of the code is going to be compiled. Okay, so this is the typical way it's used with C programming. It has advantages because the tool is always there and you can always do the thing. But for instance, in the Linux kernel that's used everywhere, that makes it possible to have this Linux kernel to be so configurable. But it has a few drawbacks. One is the fact that the main one is that once you decided that something has to be interpreted at compile time, then you cannot change your mind and decide that this feature should be actually evaluated at runtime because the syntax is different. In C, instead of having a if def, you need to have a if. And so you need to change it. So it's very difficult to change your mind about what should be decided statically and what should be decided dynamically. And further, when you have large programs, then you have this nested if-def that can go through many different files, and then in the end, you do not really understand what is there. And in a large language such as the Linux kernel, in a large program such as the Linux kernel, for instance, there are parts that basically nobody really knows why they are there and whether they are still useful, but then just in case we keep them. So, for instance, with the Linux kernel, there are about 15,000 such features, which yield a huge number of possible configuration, which is about to the, I mean, the precise number is unknown, but that's about to be 10 to the power of 5,000. Just for the record, the number of atoms in the universe is 10 to the power of 80 only. So you see that we have in computer science much bigger problem than people in physics. Okay, so this is interesting, but that's, that has a lot of limitation for actually implementing the variability. So the next idea is to try to use the encapsulation mechanism and the modularity mechanism of object orientation, like you have in object-oriented programming languages for, again, maybe 40 years now. Where you can basically encapsulate the commonality in base classes by abstracting the intent and having the specifics into subclasses. For instance, if I'm interested in a system of having something that writes something depending on some kind of a channel for the output, then I can abstract that this way by having the instruction of writing a line on an input-output, and then selecting from a language the string whose meaning is hello, for instance. And then I have this first, the modeling of the class IO with several subclasses and the languages with several subclasses. And then I can use that with the abstract factory pattern, where for each product, I'm going to have a specific factory. So I have an abstract factory that defines which part I need to build for my product, and then a concrete factory that tells me how I should build this particular variant. And then when I want to build a specific product, I just call the factory to know, depending on what is the current factory, what is the current concrete factory that is selected, which part I should build and how I should configure my software. So it works pretty well. I have this example here where I have something which is the model of a switch with a number of processing engine for the packets, the number of drivers for the interface to the networks, network managers, GUIs, and languages. And then depending on the choice I make, I can reduce by eliminating everything that is not needed for a specific product and simplify the things. So I don't know which precise I won't explain, but I obtain that kind of simplified program for that. It means that my initial program contains every possible things, and then I use this realization as a way of specializing my program to something that is smaller, that run faster and takes less footprint, less memory footprint, and less code footprint, and that can be more efficiently run, for instance. But of course, the constraint, the requirement is that I can describe my variability in very orthogonal ways that do not interact too much together, and that I can describe my product as what is called a 150% product, which contains all the possibilities. And then to derive a specific product, I just have to remove the parts that are useless for that particular product. And then it works. The thing is that when things cannot be modularized very easily, in the sense that sometimes there is cross-cutting concerns, then I need something more sophisticated, which is the notion of aspects. And that goes with modeling, because if modeling is separating aspects into different kind of concern, different kind of models, then the process of design, the normal way that you design software when you separated a number of different concerns, is to put this concern back together so that you come up with, in your head, with a design model that actually takes into account all these issues. And from this design model, you can produce the code that is needed. But of course, the idea is that these things are going to change because there is variability. So there are more than just one. And if you do it by hand, of course, you need to redo it by hand, to redo the design by hand. So the idea of model-driven engineering, of product families and aspect orientation is the idea of, instead of doing this merging, this thing that is called the weaving by hand, you're going to write a program that is going to do this weaving for you, and that takes all these models that, of course, now serve as input to a program that combine them into a design model. And that works this way. And of course, if you change your mind, you select a different variant, you just have to push the button again so that this program is going to work again and to produce a different variant. So this has very good principles because modeling is really the activity of separating concerns into aspects, and design can be really thought as weaving different concerns into something that integrates everything together into your C++ or your Java program. And basically, the recipes for doing that, they are just the well-known design patterns. And then MDE is just about mechanizing this design process, by which it's possible to change one mind on which version or which particular variant should be used. And then if I want to change something, I just push the button again. And we have shown that it can be also done and delayed until runtime. And what you get if you do that at runtime, but you get an adaptive system by you using this kind of techniques. You can really get an adaptive system that changes behavior depending on the condition you have. And you reweave your program differently, and you get a new program that adapts to different conditions, for instance. But of course, not everything is perfect. First, separating concerns of a system is not always easy. That's very difficult when the system is very complex, but that's somehow proportional to the inherent complexity of the problem at hand. But more dramatically, the thing is that this approach works extremely well when you have a small number of aspects, and when they are actually orthogonal, they do not touch the same part of the code. Because when you weave one, it works perfectly well. But the problem is that when you weave several aspects at the same place in the code, then you have a problem of composition of these things. And the big issue with this notion of aspects is that there is no well-defined way of combining them. They miss basic mathematical properties of associativity and commutativity, meaning that depending on the order by which I compose this aspect, I get a different result that most of the time is completely meaningless. And so I have to handle very specifically the way these aspects are combined. And when I do not do that, then I end up with something that is very difficult to manage. And so in the end, it's not very working. So what we want there is, after all these experiments of 30 years of trying to do that, we need something with this variability management that needs to have a separation of the description of variability from its implementation. We need to have separation of concern. We need to have modularity for the various concerns. But the composition of this concern should follow good mathematical properties. In particular, they should be commutative and associative, meaning that we should be able to compose them without thinking. And of course, they should not interfere. And when they would interfere, we should do it in a way that is explicit. And it should be possible to have late binding so that this composition is done actually in several stages during the life cycle, including at runtime. So the idea of this orthogonal variability is to have this universal variability language on the left that describe the variability. Then you have on the right side the artifacts that can be models, or software, source code, documentation, whatever. And then what you need is something that maps this variability to the base model so that you can apply that when you make a number of choice there, you can apply this selection to combine this base artifact into the product that you're interested in terms of models or in terms of software. So there have been an attempt during the year 2005 until 2012 about something that was called the Common Variability Language that was supposed to do that. But it did not work that much, essentially because it was a low-level realization language, working at very low level, and you need to really understand what was going on at the level of either the model elements or the object in an abstract syntax tree to be able to really work with that. So it was really like an assembly language for doing that. And so it was very difficult to use. So the vision with the Universal Variability Language is to provide something that is modular, that is there as a community effort to simplify the exchanges of these variability models, and that provides some tool support to make a number of computations. And for me, the good points of the Universal Variability Language is that it is a fully declarative language, which is formally defined, unambiguous, but that is very human readable. You can really see that as the list of features, whether they are mandatory, optional, with alternative, and so on. It's a declarative specification of product variant without prescribing any implementation, and it can work in any environment with any kind of technology. And it is model-based. By applying principle, you can analyze them and generate things. And another good thing is that it has a two-level modularity, one at the level of the model, and which is where you can import modules to compose properties out of smaller things, and at the language level, where you have something that works with the core level, which is basically feature diagrams. You can have Booleans, but you can also add arithmetics, operators, and even types, so that you have a type object pattern into this language. And so for that, the missing link is, of course, this thing, how you go from this variability description to the artifact to get your product. And this is what is called in the product line community, the realization of that. And so we need a realization language. And for that, it's a kind of holy grail, for taking that. And we propose a language that is both declarative, high level, and independent from any specific industry or tool support, and that also supports stage configuration down to runtime to make the connection with the notion of feature toggle, which is really this notion of feature that you select or unselect at runtime. So the key feature is that first, it is a generic high-level language where the concept of the meta model of interest, which is the language of interest, can be manipulated directly. So if you manipulate classes, attributes, and method, that's the things that you're going to have in your language. Or if you're with a state chart, for instance, you're going to manipulate state and transitions. Or if you're with BPMN, you are going to manipulate processes and gates and the like. And the thing is that all meta classes of these languages, of this meta model, are imported into a GREAL model. And you have a kind of function that gives you all the objects or the instances corresponding to that. For instance, in UML, you have something that is called class, and that returns all the classes. And you can filter with a number of, with regular expression based on attributes, such as the name of the class or something. And then the language is declarative, supporting both positive and negative variability. Negative variability is the thing that I want to remove from my artifacts, and the positive variability is the things that I want to compose. Composition is based on a unification of matching elements, meaning that two elements that have the same name are going to be unified into something that only exists once. Negative variability is considered after positive variability is done by removing everything that is not needed. And there is a possibility of feature assignment, meaning taking attributes from the feature model, from the variability model, and putting them into the base model. And feature interaction are dealt explicitly. So to take a very concrete example, I take something that is the expression product line. The expression product line is just the idea that you have a small grammar that makes it possible to manipulate literates, numbers basically, and having the possibility to add them and to make negation. And then, so you have as featured different type of things that exist in your language, such as, constant addition or negation, and then operation such as printing the expression or evaluating the expression. And this example is very short and very simple, but it has the interest of showing something that cannot be readily implemented with an object-oriented languages because there are cross-cutting concern between features, function on one side, and the typical way of implementing it would be classes. So the base models, they look like that. So you can display them using UML or using Java program. That's exactly the same. Your base model is just the class expression that has a subclass, a literal, which is a value. And then there is a factory. I will get back to that later. And for instance, if you want to add the feature evol, then you have to describe that there is a new method called evol in the class expression, a new method called evol in the class lit that would return, the value that is stored. And for instance, there is this add method, which is the fact that there is a new expression that is called add, and that has the method add as a left-hand side and a right-hand side, and can print something and create an add expression. And then we describe how it works when you combine add with evol by having this thing that must be added, where you have this evol method that is added to the class add. And the way it works is that you have this realization language where you import your feature model, which is this description of basically this thing, which is there. You import your base model here, there, and then you describe that when add is selected, when the feature add is selected, then you import the part of the model that is needed. When the eval is selected, you import the part of the model that is needed with some unification. And then when both are selected, you import the part that describe how they should be combined. And you can add something which is a negative variability. For instance, if print is not selected, then you remove within the API model all the methods that are called print. Okay, so it works this way. If you put everything together, then you have this top-down evaluation that actually, depending on what is selected, is going to compose the program that you're interested in. The derivation algorithm, shortly speaking, is first to resolve the positive variability by composing things together and having a unification on the name. Then resolving the negative variability, which is the phase two. The phase two, you remove everything that is not needed, and then you resolve the value assignment with a caveat, which is the fact that, of course, if you want to be composable, there should be only one assignment, because otherwise the result would depend on the order. And so this could be mitigated a little bit by considering that assignments are only relative, which is very useful in many situations, meaning that if it is an addition, it's actually not assigning the value 3, it's adding the value 3 to the current value. And multiplication is the same. And then, as a last resort, you can basically follow the developer order, but then you lose the composability. And then there is a last phase, which is the model normalization by cleaning up or applying style rules that are needed. So the result of that is that when I select add and evol as features and I unselect neg, then the result I get is this particular model with this particular part coming from the various pieces. Okay. So we'll skip that, how the thing is done, the language is done, so I will skip it. Just to say that there is the possibility of having stage configuration. We can run multiple steps, which is very convenient in the case of a product line. And if the last step is not resolved, then we can actually generate code that works with feature toggles. so I will not have time to explain that because I took too much time to explain the rest. But basically, if you're interested in that, there is a paper that describes how you go from feature in the sense of universal variability language to these things that are the feature toggle that are used at runtime. So we'll just keep that. So this work with a UML diagram, but it also work with plain text. For instance, if I have the documentation of my product line here, by having the various part of my documentation, each one is describing a part of it, then I have the exact same kind of realization where I import this thing, I import the text, and here the text is basically seen as a list of lines. And then I can mix if add is selected, then I will change the thing by composing add this text with this one by having the unification on the content of the lines. And so it will give this new documentation for that particular product when I select that, and I see that my text is woven into the base text that is there. Just to give you an idea, the driver for doing that for text is about 100 line of code. It's actually written in Python, and it's very simple to write. So to see whether it works in practice, we did that as a large-scale experiment at Airbus, where they actually use something that is called a program development plan when they want to build a new aircraft. Of course, building a new aircraft, it's a huge endeavor. You need to think about the way you're going to build it. You need to build first the factories, and because it is Europe, parts are built in many different countries across Europe. So you have to come up with a workflow. Where are the parts? How they're going to be assembled, and the like. And for that, they are using BPMNs for describing the way it works. But where they are starting a new aircraft, actually many decisions are not yet made. Where is going to be the factory, whether this particular part of the aircraft is going to be built by Airbus or by a subcontracting, or is it going to be bought from some supplier. So there are many possible decisions that have an impact on the workflow. And we described that experience with this particular paper here at Models 23. The thing is that they wanted to capture alternatives so that they could find scenarios where they would try to minimize, for instance, the lead time, the total time it takes to produce a new aircraft, or the cost, or there are many other factors of interest where they want to do that. And so the idea is to model the business process as a product line using orthogonal variability like we have shown before. And because there are many different options, then you can simulate what's going on and know in advance how much time it would take if we choose that particular option, or what would be the cost and so on. And then because if it is fully automatic, what you can do is to run search-based algorithm to optimize with respect to the lead time or things like that. So what we did is to model using BPMN the various possibilities of the choices, and depending on the choice, produce automatically a specific business process model for that, and evaluate issues using this BPSIM simulation framework, evaluate how much time it takes to produce this new aircraft, for instance. And so the idea, I mean, this is very simplified here. That's of course, that's a huge thing, and we only were allowed to publish a very limited sub-part of it. But here, for instance, depending on the choice they make for this new aircraft, whether it's going to be quite nominal, I mean, reusing many parts and many previous processes, or whether it's going to be conservative, which is basically just an evolution of an existing aircraft, or completely differently if it is going to be innovative, because, for instance, instead of having a normal engine, it's going to be an electric engine or something like that, then the process is not going to be the same. And we describe what is the impact on terms of the business process of that. And using this GREAL language, we describe that when we select the base model, then we do that and that, and depending on the choices that are going to be made, then the process is going to be changed this way by reusing these blocks and removing this part that is no longer useful and the like. And so from these basic building blocks, we build more complex processes that are assembled to describe the full product development plan of a large scale thing such as a product development at Airbus. So this is an example of the actual code that is there that describe how many tries, for instance, and how many validation loops you need to do depending on the condition of what you have. So this is an example of the very same language. I mean, the first case was to apply it to a normal software engineering problems and to text, and now with BPMN, with business process models for doing the same thing. And so it produces that, for instance, where you are there. So it is used operationally at Airbus for 3 years now. Well, there are some specific things. There are interesting lessons that are learned from the way we work with them. First, negative variability provides an exhaustive view on the possible alternative, but the overall model is too complex to be maintained because nobody any longer understands what's going on. Positive variability makes it possible to combine individual parts from the assets, but then the composition operators, you have to think about them, so it's not always there. And so the proportion of positive with respect to negative variability, this is something that has to be investigated and that has to be defined as a methodology to reach the right level of complexity for doing these things. And of course, we do not, I mean, GREAL is a language for doing that. It's not a method. So, I mean, each industry needs to find the proper way of finding the good trade-off between negative and positive variability. But then the full automation of that made it possible for them to use these search-based approaches to optimize some criteria and to automatically design the processes that optimize some specific criteria. Okay, so takeaway messages because I'm a little bit late. GREAL is a generic realization language for making the connection between the variability language that describe the possibilities, the variability possibilities, and the base assets that represent your software, your components, the thing that you have, so that depending on the choice you make, a given product can be obtained automatically. The thing is that GREAL is independent from a specific, base language. It can be used. I mean, we have demonstration of using it with UML or any kind of EMF-based meta model, with plain text, with BPMN, and of course with Java, because somehow an abstract syntax tree is just a meta model. As perspective, it's still a research project in a sense, because the text that you find here for describing GREAL products is actually a DSL that is very good for us because we are computer scientists, so we understand what is there. But the people describing these things at Airbus, they are not computer scientists, they're aerospace engineers. And for them, that level of language is not that meaningful. So we should find new way of expressing the same thing in things that they can understand. And so this is still work in progress for that. And to find the proper form for this language, we think that we have the right concept for doing it, but the proper form still has to be invented, maybe with a better DSL, or maybe just with an API that you use a normal programming like Python for driving this API, or even because these people, they are used to Excel, how you could express this concept of Excel, within Excel, which is feasible because basically you describe on the line, for instance, what you do when a specific option is selected, when a specific feature is selected, and you describe in the columns what is going to be done for that particular part of the software. So that could be even driven by some Excel spreadsheet. So this is another possibility. Okay, so a few references for supporting that with these two papers there. Okay, thank you very much for your attention. If you have any question, I'm happy to answer them.
Any questions from the
I stop,
attendees?
I stop sharing.
So thank you, Professor Jezequiel. It was really very insightful. In the meantime, while the audience thinks about questions, I'll probably ask you a couple of questions of what I myself have.
Sure.
So, so the application in aerospace industry is interesting, but can GREAL be applied in industries outside automotive and aerospace industries as well?
Yes, because it's supposed to be completely agnostic of the kind of languages that you use. So you can see GREAL as a language for the composition of artifacts, and whether the artifacts are described in Java or in plain text or in XML or in BPMN or whatever. For GREAL, it's exactly the same thing. So the interesting part is that it makes it possible to combine element of languages or artifacts that are not that were not designed to be combined. And so it works very well for, let's say, languages such as BPMN, because BPMN does not have good mechanism for modularity, for reuse, for describing variability. So we start really from scratch with that. If you're already using something like Java and you're able to modularize your variability by saying that everything is encapsulated in subclasses, for instance, as the example I showed earlier, then you do not need it. And sometimes you only need it for cross-cutting constraint or the like. But since in my experience with software, it's sometimes it's so complex that having a mechanism to be able to compose the various parts depending on a high-level selection, which is the variability, is very useful. So right now, it's more used in system engineering, I would say. So in the automotive industry, it's there with languages such as SysML. It's also used with BPMN and the like. But there is no reason it should not be used with software, even if with software we already have some tools for doing that kind of things. We have, I mean, I've shown this if-def or the composition in object-oriented languages that goes already toward this direction, but we think that GREAL is the step after that that also should pay off in any software-based industry, I would say.
Thank you. I don't see any questions in the chat window. There's just a comment thanking you for the talk. So I'll probably ask one more question.
Sure.
So what are some of the challenges in managing variability across different industries?
That's an interesting question, because there is something which is very strange, is the fact that when you talk to high-level management, they know what is a product line. I mean, if you talk at Airbus or at Boeing, it's the same. I mean, what is your product line? Well, we have this product line of small aircraft, big aircraft, and the like, and within the A350, for instance, there is all these variants that depends on the company. So they pretty much aware of what is a product line. From the marketing point of view, any company, if you go to the marketing, they know what is a product line in any industry, whatever it is. I mean, whether you produce perfume, whether you produce software, whether you produce cars, whether you produce whatever, everybody's in the marketing department knows about what is a product line. The funny thing is that if you look at the development part, people know about variability because from the bottom, variability, you handle that with, subclasses or if-def or whatever. So you know that. But then making the connection with the department, with the marketing department in this part, it's not always the case that industries are able to do that. So some industry did it in the past. For instance, in the cell phone industry, it was a cornerstone of the power of the Nokia and the Siemens and the Samsung of the world to make this connection very early there. But for other industries, sometimes it's quite difficult. I mean, if you look at pure software things such as the Linux kernel, we have been working a lot with people in the Linux kernel with these variabilities everywhere. The implementation is very low level, and then when you try to reason, you have to reconstruct with this config thing that describe the variability. You have to reconstruct and to translate it somehow into a variability language, and to have to show that some options are actually mutually incompatible or the like. And you can really work at that level of abstraction. But the funny thing is that this connection between this high level view of what is a product line from the marketing or the high management, there is a big gap with the technical part that actually handles that. And all these efforts of software product lines and variability management are really a way of bridging this gap between these two views in a company, between these two views of the world, basically.
Yeah. Thanks for those insights, Professor. It was really very interesting presentation. I'd like to present, now that we are at the top of the hour, I just wanted to present this certificate. If it was an in-person event, we would have presented you with some memento, but because this is remote, I just wanted to present this certificate as a small token of our appreciation for your time today and the insights that you shared. So hopefully, if you are visiting Bay Area, let me know, and we can probably organize something in person next time.
Thank you very much. Thank you very much for the certificate.
Yeah. Thanks everyone for joining. I think we can end our meeting here, and hopefully see some of you in the next event.
Thank you very much.
Thank you.
Bye.
Bye.